Hello dear students, so today we will discuss a concept from electrostatics, that is torque on an electric dipole placed in an electric field. Okay, so for this let's consider that a dipole consisting of minus q and plus q charge is placed in an uniform electric field. Okay, so this is the electric field direction. The dipole is placed in uniform electric field of magnitude E, and at an instant, say the dipole moment is making an angle theta with the electric field vector. And for this, suppose that the two charges is placed at two different points. Consider that the point is A and this point is B, and in between A and B there is a middle point, say O, and consider that the distance between A and B is D, and O is the midpoint of A and B. So we have to calculate the torque experienced by the dipole which is placed in electric field. For that we have to consider the force acting on plus q charge and minus q charge. Okay, so the force which is acting on plus q charge is suppose F1. So the force will act in this direction because the electric field direction is this direction, and on minus q charge the force will act in this direction. Suppose that the force is F1 and the force acting on minus q charge is F2. So the force F1 is given by Q into E, and in the same way the force F2 is also given by minus Q into E. Now we have to calculate the torque. So due to these two forces, the electric dipole experiences a torque. So the torque tau 1 for force F1 about point O. So we are calculating the torque of F1 about point O. So what is that torque? So the tau 1 will given by R cross F1. So R is the vector from O to the point where force is acting, and F1 is the force. Okay, so we can write this as R cross F1 is nothing but Q cross E, and the R for O to B is OB, we can write, okay, cross Q into E. Okay, in the same way tau 2 of force F2 about point O. So the F2 will given by R cross F2. Okay, so the R is nothing but OA cross F2, and the value of F2 is minus Q into E, and this equation is also can be written as Q into AO cross E, because the minus sign is replaced by the change in OA to AO. So that is the value of torque 2. So the net torque is given by tau is equal to tau 1 plus tau 2. Okay, so the value of tau 1 is Q OB cross E plus Q AO cross E. Okay, so now the torque is Q OB plus AO and cross E. Now from this diagram we are aware that the OA plus OB is AB. So in place of OB plus AO, we can write AB. Okay, so torque is QAB cross E. And we have considered that the value of AB is D. So the torque is given by QD cross E. Here the quantity Q and multiplication of D is given by P, which is called dipole moment, So the tau can be written as P cross E, where P is electric dipole moment. This is the expression of torque experienced by electric dipole, which is placed in uniform electric field of magnitude E. The equation can also be written as Pe sine theta, where theta is the angle between line joining AB point and electric field vector. Okay, so in a conclusion, we can say that the torque is act perpendicular to the plane containing the line joining point A and B and the electric field vector. Okay, so here we can write that the torque is perpendicular to the plane containing axis of AB and also electric field vector. Okay, so let's solve a numerical problem based on this concept. So this is the problem that we'll discuss. Okay, so in this problem, the question is, figure shows an electric dipole formed by two particles fixed at the end of a light rod of length L. Okay, according to the question, there is a dipole, okay, formed by two particles. Okay, so let's consider that the dipole is minus Q plus Q, and there is an electric field. Okay, at ends of a light rod. Okay, so this is a light rod, and end of this there is two particles, minus Q and plus Q. The mass of each particle is m, so the mass of each particle is m, and the charges are minus Q and plus Q. The system is placed in such a way that dipole axis is parallel to a uniform electric field. Okay, so parallel to this axis there is uniform electric field, okay, of magnitude E that exists in the region. The dipole is slightly rotated about its center and released. Okay, so this dipole is rotated about its center, so this is the center, and dipole is rotated like this, okay, at a small angle. Let's consider theta. Okay, rotate this. So that for small angular displacement, the motion is angular simple harmonic, and find its time period. Okay, so there's two questions. First of all, we have to show that the motion when it is rotated about a small angle, the motion is angular simple harmonic, and also we have to find out its time periods. So let's discuss how to solve this problem. Okay, so for this, first of all, solution. Okay, we have to find out the torque experienced by the electric field, experienced due to the electric field by the dipole. Okay, so the torque is given by P cross E. Okay, so P is the distance between two charges and one charge. Okay, so Q into the distance between two charges is given by L. Okay, so L into cross E. Okay, or we can write Q L E sine theta. Okay, by the expression of torque. Now if we rotate by a small angle, okay, so we can write sine theta is approximately equal to theta. So when the electric dipole is rotated by a small angle theta, the torque which is acting on electric dipole will tend to rotate back the electric dipole towards the electric field direction. Okay, so the torque is again can be written as minus q L E and theta. Okay, so this is the equation of torque which is acting in this scenario. Now we know that the angular acceleration is given by alpha is equal to tau by I, where I is moment of inertia. So to find out the angular acceleration, we have to find out the moment of inertia of the system. So the system looks like minus q, and there is a rod and there is plus q, and the mass of these two particles is m and m. So the moment of inertia along this axis is given by I is equal to, okay, and the length of the dipole is L, so the half length will be L by 2 and L by 2. So I is equal to m L by 2 square plus m L by 2 square. So calculating I is equal to m 2 times L by 2 square. So it is m L square by 2. Okay, so this is moment of inertia of the system. So we can find out alpha is equal to tau by I. It is tau. Okay, so the value of tau is minus q L E and theta. Minus q L E and theta, and the value of I is m L square by 2. Okay, so this we can also write minus q L E theta into 2 upon m L square. So this L. So alpha is equal to minus q E or 2 q E theta upon ml. Okay, but there is also an equation that alpha angular acceleration is minus omega square into theta for angular harmonic motion. Okay, so comparing this equation with this equation, we can conclude that the omega square is nothing but 2q E upon ml. So we got the value of angular frequency. Okay, so we can say that the motion is angular simple harmonic. Okay, you can also find out the value of omega, which is root 2QE by ml. Now it's time to find out the time period. Okay, time period. So the time period t is given by 2 pi by omega. Okay, we have omega, so from omega we can find out the value of t. So t is 2 pi upon the value of omega is 2QE upon ml. 2QE upon ml. So t is 2 pi into ml upon 2QE. So this is the value of time period for this question, 2 pi ml 2QE. Okay, so in this way we can solve the numerical problem based on the this concept. Okay, so that's all for today. Thanks for watching this video.